All right, we are on the very last skill of second semester of Algebra 2, and this is the tools of rational function analysis. So when you get to pre-calculus, you'll be able to actually create perfect graphs of rational functions, and we're going to give you most of the tools today and what they look like. One of the first tools is looking at where we have x's and y intercepts. And it's just like in linear and quadratic type of situations. X-intercepts are where the graph hits the x-axis. And then y-intercept is where the graph hits y-axis. And we're just going to go and put those. So let's see, we got a x-intercept here. And you can put them in the coordinate form. And we actually just have one x-intercept, so that would be at, in this case, 5, 0. And then the y-intercept takes place at 0, -2. Then we have something that's called a vertical asymptote. We abbreviate that as VA, and it is a vertical line showing where function is undefined. And there'll be kind of a more precise definition when you get into pre-calc or calculus. And the vertical asymptote takes place in this function at x equals to -3. Horizontal asymptotes, that will kind of take place and get more precise a little bit later. But we can say that this function has a horizontal asymptote at y equals 1. And then the whole is what we call kind of a removable discontinuity. So continuity just simply means, can you draw the graph without picking up pen? And the asymptotes, there's kind of skips in the graph, but a hole, if you filled in the hole, the graph would be continuous. And we would say that the hole in this case is right there. And it is, a point of discontinuity. And it would have a coordinate of 2, -1. So those are some features of graphical analysis, but I claim that you do not even need a graph to figure out most of these things if you know what to do with the rational expressions. All right, so the first thing that we're going to be looking at are these vertical asymptotes. So to find a vertical asymptote, you factor the denominator and you set the factor of the denominator equal to 0. So I like factoring. So when I do this, I have a difference of 2 squares on the top. So I'm just going to actually factor that. So let's see. My first term would be 3x. My second term, I'm going to do the square root of 25, which gets me to 5. So the top is a difference of squares. That's what I'm doing up there. And I would get 3x plus 5 times 3x minus 5. And then on the bottom here, I can take out like a GCF. And I can also do ACB chart. Obviously, you want to do the GCF so that your ACB chart can be a lot more reasonable. So what I can kind of see here at a glance is that 3 goes into 9, 78, and 105. So if I just kind of focus on the denominator, I'm going to pull out a 3. So 3 times 3 is 9x squared. And then if I do 78 divided by 3, that's going to be 26x. And if I do 105 divided by 3, that's going to be 35. So I'll need to do my ACB chart. So let's see, 3 times 35 is 105, and I need 105 add up to 26, multiply to 105. So obviously like 1 and 105 doesn't work. Oh, actually, I'm going to do, yeah, 1 and 105. That does not work. Maybe I'll try like 105 and 3. So like 3 and 35, that does not work. And then maybe I could try but then 21 and 5 does work. So when I do that, I get 3x squared plus 21x plus 5x plus 35. And I can kind of group these, so I could pull out a 3x and a 5. So at the end of the day, when I factor, I have a 3 times 3x plus 5. And let's see, when I pull out a 3x, I'm going to have x plus 7. And we want to kind of read our terms and conditions here. So it says, if the factor is in both the numerator and the denominator, it is a whole. So it's not a vertical asymptote. These factors go away, but we can say that there is a VA when x plus 7 equals to 0. And that means that x is equal to -7, and that is where our vertical asymptote is. So you are going to be kind of spending the brunt of the work with the factoring process. This one actually kind of had a harder difference of 2 squares example, ACB chart, but you had to pull the GCF. So we kind of did give you the whole gamut of factoring. But if you kind of look at the denominator factors, you set the denominator factors equal to 0, and make sure that you're not choosing factors that are in both the numerator and the denominator. The vertical asymptotes are very doable. X-intercepts. So this one actually, and you'll kind of see mixed in your delta math. There's going to be ones that have factoring and then ones that don't have very much factoring. But I will say that you could use the numerator factors to determine the x-intercepts. So what that means is that I'm going to set 0 equal to x minus 3. So if my numerator is equal to 0, then I can find out what my x-intercept is going to be. So I'm going to add 3 to both sides. And they want a coordinate point. So if I want to know what my y coordinate is going to be, I just plug in my 3 for x. Three plus 10. Obviously, my y coordinate is going to be 0. So I'm actually going to assess your knowledge of intercepts on the final exam by having you look at a rational function like this. Because the rules are pretty much the same. So to find those x-intercepts, you're going to set the factors equal to 0 in the numerator. Now let's look at y-intercepts. Actually, let's kind of look at an x-intercept with factoring. This one, the factoring is not as bad. So we have ACB on the top. We have a GCF on the bottom. So when I factor, I know that I have x times x. And I want, two numbers that multiply to 72 and negative 72 and add to 1. So maybe I would have plus 9 and minus 8. And then I'm going to pull out an x on the bottom. So that's going to be x times x minus 2. So I'm going to say that x plus 9 equals to 0. And x minus 8 equals to 0. That makes that x equals negative 9, giving us the coordinate of negative 9 comma 0. And this is going to give us x equals 8, giving the coordinate of 8 comma 0. And that's how I can find my x-intercepts. Now, let's look at some y-intercepts. So the y-intercept, that's even easier. All what you have to do is just plug in 0 for x and kind of see what happens. And you're not always going to get a y-intercept. And let me just change the directions on that. And lo and behold here, we get a divide by 0. So what happens here is that there is no y-intercept. And actually, we would find that it would be a vertical asymptote. I wanted to kind of use like the same function, just so you could kind of see. Now, if we had a y-intercept, we'd get like some type of real number in the denominator. And then finally, we have wholes. So this you do want to like factor your numerator and denominator. So I'm going to pull out a GCF of 3x. It's going to be a x minus 4 because 3 goes into 12 4 times. And then on this one, I have a 5 times x minus 4. And what I notice is that there is a x minus 4 in both the numerator and the denominator. Making it a whole. So I'm going to set x minus 4 equal to 0. And then I'm going to plug in the x coordinate into the canceled version. So I'm going to have 3 times 4 over 5. So that's going to get me to 12/5. So the y value of where we would be at 12/5 if the function was defined. But because it's a hole, it's going to be like a circle. So like when we have a hole, you know, we would think that the function would be defined, but it's not defined. But we can kind of see that right around it, it's going to kind of have that approximate y value. So those are some tools of analysis of rational functions that you're going to see. And the good news is that you're going to kind of see this stuff over and over again in this type of terminology in pre-calculus with all sorts of different types of functions.